The universe is not expanding at a steady pace. Even now, in this quiet moment, space itself is stretching faster than the speed of light, carrying distant galaxies away in a motion so gentle we cannot feel it, yet so immense it reshapes the destiny of everything that exists. What seems still and silent around you is part of a vast, accelerating drift, a cosmic breath woven into the fabric of space-time. Before we drift into that expansion, if this calm journey brings you even a moment of peace, I'm deeply grateful you're here. Your gentle like, your soft tap on subscribe, helps this quiet corner of the universe continue glowing. Thank you for being part of it. Now, we drift into Part 1. Part 1. Why is the universe expanding at all? In the earliest moments after the Big Bang, the universe was not calm. It was a hot, dense ocean of energy where space, matter, and time were still taking shape. And yet even then, expansion had already begun, an outward motion so persistent that it continues today. To understand why the universe expands, we must return to that first instant when pressure and energy density wrote the very first instructions for cosmic motion. The first truth we face is that expansion is not an afterthought of the universe. It is its foundation. The Big Bang was not an explosion in space. It was an explosion of space, a moment in which every point erupted away from every other, not through a void, but through the creation of the void itself. Even now, as you sit here breathing gently, the same rule is still unfolding. Space is stretching in every direction around you, though so subtly that nothing in your body senses it. The expansion is too smooth, too uniform, too vast to be felt locally. But on cosmic scales, its effect is unmistakable. To understand why expansion began, we must begin with energy. Not the energy of motion, but the energy of existence itself, the dense primordial pressure locked into the universe when it was smaller than an atom. According to general relativity, energy determines the curvature of space-time, and in the early universe, the energy density was so enormous that space-time curved outward, pushing everything apart. Expansion was not a force acting on the cosmos. It was the natural response of space to the unimaginable pressure of creation. Imagine something as small as a proton suddenly filled with energy so intense that the very geometry of space can no longer hold still. That was the early universe. A fraction of a second after the Big Bang, temperatures climbed above 10 trillion degrees. At those energies, matter and radiation were indistinguishable. Photons behaved like particles, particles behaved like waves, and all of it churned in a seething plasma where no stable atoms could form. This was not chaos in the way we imagine it. It was the most orderly kind of chaos, the kind described by physics at its most fundamental level. In this glowing furnace of creation, space did something remarkable. It didn't attempt to contain the pressure. It yielded to it. It stretched. And as it stretched, the density dropped. Just like air inside a balloon cools as the balloon expands, the universe cooled as it grew. Expansion and cooling are inseparable. One allows the other. And as temperatures fell, the universe passed through a series of quiet thresholds where new structures could form. Quarks slowed enough to bind into protons and neutrons. Later, protons and electrons combined into atoms. These atoms became the seeds of stars and galaxies. All of it unfolded because the universe kept expanding. But what initiated that stretching? What wrote the first instruction? Expand. Here we turn to inflation, one of the most astonishing ideas in modern cosmology. Inflation describes a moment, far earlier than even the first second, when the universe underwent a burst of expansion faster than the speed of light. This is not poetic exaggeration. It is a consequence of Einstein's equations. Space itself can stretch faster than light because nothing moves through space at that speed. The fabric simply widens beneath everything within it. During inflation, the universe doubled in size again and again in unimaginably small fractions of a second. A region, once smaller than a proton, ballooned to macroscopic scales, and the energy field that powered inflation, called the inflaton in theoretical models, filled space with a gentle, uniform pressure. That pressure pushed outward evenly, smoothing out the cosmos until everything, matter, radiation, and geometry, became nearly identical everywhere. This smoothing explains why distant regions of the universe, separated by billions of light years, still share the same temperature and density. Without inflation, they shouldn't. They would never have been close enough to exchange information or energy. Inflation ties them together through a shared origin, a moment when everything was close enough to interact before being flung apart. When inflation ended, its energy didn't disappear. Instead, it transformed into the matter and radiation that fill space today. And the expansion it began never fully stopped. Inflation set the direction, and the universe continued drifting outward on its own inertia. After inflation, the expansion slowed dramatically, softening from an almost violent surge to the gentler, steady stretching we measure today. As the universe cooled, it transitioned through phases that shaped everything we now observe. When protons and electrons finally combined into neutral hydrogen about 380,000 years after the Big Bang, the cosmos became transparent. Light from that moment, the cosmic microwave background, still drifts across the universe, carrying within it a map of the universe's earliest structure. That ancient light shows us something extraordinary: slight ripples in density, 1 part in 100,000. These tiny fluctuations, amplified over billions of years by gravity, grew into galaxies, stars, planets, and eventually into every living thing. But none of it could exist without expansion. Without that initial stretching, matter would have collapsed into a uniform, featureless soup with no structures, no stars, and no life. Expansion created the room for complexity. As billions of years passed, gravity began shaping the slow dance of matter. Galaxies formed, collided, merged, and evolved. The expansion of the universe continued, but gravity acted as a counterbalance, drawing matter inward to create dense objects surrounded by emptiness. This tension between expansion pushing outward and gravity pulling inward defined the history of the cosmos. For a long time, scientists believed the universe might eventually slow down. Maybe the expansion would halt. Maybe everything would collapse back in a big crunch. But in the late 1990s, astronomers discovered something unexpected. The expansion was not slowing. It was speeding up. Galaxies were receding faster than models predicted. Some quiet, invisible pressure was pushing them outward with increasing strength. That something is now known as dark energy. It is not a traditional force. It's more like a property of space itself, an energy that appears uniform everywhere and acts as a kind of negative pressure. As space expands, more space forms, and with it, more dark energy. This creates a feedback loop that accelerates the expansion further. Though dark energy dominates the universe today, the earliest expansion did not require it. The Big Bang itself and the energy density of the early universe were enough to drive the initial outward push. Expansion is woven into the equations of general relativity. It is the natural state for a universe filled with energy. So why is the universe expanding? Because energy bends space. Because the earliest moments set a trajectory that has never changed. Because inflation created a motion that could not be undone. And because empty space itself carries the quiet push we call dark energy. Even now, as you breathe gently and feel perfectly still, galaxies billions of light years away drift ever farther, carried by this ancient, enduring motion. Expansion is not something the universe did once. It is something the universe is. A continuous unfolding, a slow softening of density, a cosmic exhale that began in fire and continues in silence. And as we follow this gentle outward motion, one question naturally rises. If space itself is stretching, then what exactly does that stretching mean? Part 2. What does it mean for space itself to stretch? When astronomers say the universe is expanding, they don't mean galaxies are rushing through space like shuttles. They mean space, the very stage on which all things exist, is stretching beneath them. This stretching is slow here, fast in the distance, and invisible everywhere, a quiet rearranging of cosmic geometry that carries worlds farther apart without a single gust of wind. To understand this, You must imagine something subtle, not motion through space, but motion of space, a shifting of the grid, the scaffold, the very fabric upon which galaxies rest. In ordinary life, space feels rigid and empty. You move through it, it does not move around you. But on the largest scales the universe knows, space behaves differently. It bends, it curves, and across billions of light years, it stretches. This idea comes directly from general relativity, Einstein's vision of gravity not as a force, but as the curvature of spacetime. According to his equations, space isn't a passive emptiness, it's a dynamic, evolving structure. In areas of high mass, it folds inward, creating gravity wells. In the absence of mass, it behaves like a smooth sheet, and when filled with a uniform energy, like dark energy, it stretches. But what does stretching even mean? Imagine a simple grid drawn on a rubber sheet. Each square on that grid represents a region of space. If you place small dots on the intersections, these are your galaxies, they will appear fixed. They don't crawl across the sheet, they rest on it. Now gently pull the edges of the sheet. The dots drift apart, not because they move, but because the fabric between them widens. That widening is expansion. This comparison, though simplified, captures one essential truth. When space stretches, distances increase even if nothing travels those distances. A galaxy, 1 billion light-years away, becomes 2 billion light-years away, not by moving, but by being carried outward on an expanding sea. This effect is nearly immeasurable on small scales. Here in the solar system, the sun's gravity is strong enough to bind Earth tightly in orbit. No cosmic stretching tugs us outward. Even atoms are immune. Electromagnetic forces hold them too tightly for expansion to pry them apart. Space stretches only where gravity is weak or diluted, across the vast emptiness between galaxies. The stretching of space reveals itself most clearly in light. As photons travel through expanding space, their wavelengths stretch with it. Light that leaves a distant galaxy starts its journey bright and blue, but arrives tens of billions of years later stretched into red, then infrared, then microwave wavelengths. Astronomers call this redshift. It isn't caused by speed in the classical sense. It's the universe growing beneath the light, pulling its waves into longer, softer forms. When we measure that stretching, we are measuring expansion itself. But to truly see what this stretching means, we must go deeper into the way cosmologists visualize space. They think not in terms of voids, but in terms of metrics, the mathematical rules that define distances. In our everyday intuition, the distance between 2 points is fixed. A meter is a meter. A kilometer is a kilometer. These units seem eternal. But in the expanding universe, the very definition of distance changes with time. This is why cosmologists distinguish between 2 kinds of distance: proper distance, the actual length at a given moment, and co-moving distance, the distance scaled by expansion. In co-moving coordinates, galaxies never move at all. They sit motionless, embedded in the fabric. But proper distance grows because the scale factor, the metric that determines the size of space, grows. The scale factor is the quiet heartbeat of the cosmos. It tells us how large the universe is compared to any earlier time. When the scale factor doubles, every large-scale distance doubles. When it triples, the cosmos is 3 times larger. And because the scale factor increases faster and faster due to dark energy, space is stretching more aggressively now than in the past. You can think of the scale factor as a cosmic rhythm, slow and steady, unfelt locally, yet immense in its accumulated effect. Its increase does not speed up planets or tug on stars or twist galaxies out of shape. It acts only on the vast lanes of emptiness between galaxy clusters, changing the architecture of the cosmos while leaving the small structures intact. Astronomers observe this stretching through the Hubble-Lemaitre law. The farther a galaxy is, the faster it appears to recede. This relationship is not a measurement of motion, but of distance multiplied by expansion. At a few million light years, recession is slow. At hundreds of millions, it becomes noticeable. At billions, it accelerates beyond anything possible for objects moving through space. Expansion is not limited by the speed of light because it is not a speed, it is a change in scale. And that leads us to a strange consequence. Beyond a certain distance, galaxies are receding faster than light simply because the fabric between us expands faster than any photon can cross. The universe is not breaking its own speed limit. That limit applies only to objects moving through space, not to the rate at which space itself can grow. To many listeners, this idea feels deeply counterintuitive. Our senses evolved to interpret motion in rigid, stable environments. We feel acceleration, not constant drift. We notice forces, not changing geometry. If space stretched by 1% per century, your body wouldn't notice. But across billions of light years, such a small rate becomes enormous. This is why astronomers speak of the metric expanding rather than objects moving. It's a reminder that on cosmic scales, distance behaves differently from how we experience it in daily life. But space does more than stretch. It carries the past within that stretching. Every photon traveling through the universe is affected by the scale factor. If the scale factor doubles during a photon's journey, its wavelength doubles. Every bit of cosmic microwave background light we observe today is stretched by a factor of more than 1,000, transformed from blistering radiation into a cool whisper of microwaves. This cosmic stretching is a record of time itself. When you look at a distant galaxy, the light you see left it billions of years ago, but the galaxy is now far more distant than it appears. You are seeing the universe not as it is, but as it was. Stretching space turns the cosmos into a time machine. Every photon is a story carried across an expanding ocean, and yet, despite this stretching, the universe feels still to us. We do not sense the expansion. The silence of it, the uniformity of it, hides its scale. But expansion is always there, woven into every moment. If you could look beyond galaxies, beyond clusters, beyond the filaments of cosmic structure, you would find a universe not exploding outward, but simply growing, softly widening in every direction. Not a storm, not a wind, but a gentle loosening, the grid expanding under its own laws. And so, one quiet question naturally follows. If space stretches everywhere, why do some regions resist that stretching and remain tightly bound? Part 3. How can something expand faster than light without breaking physics? The speed of light is a boundary for objects moving through space, but when space itself expands, that boundary doesn't apply. Galaxies carried by expansion can drift apart faster than any photon could chase them, not because they exceed nature's limit, but because the fabric between them grows. It's a distinction subtle enough to feel like a paradox, yet precise enough to define the shape of the observable universe. To begin unraveling this, you must first remember that the speed of light, 299,792 kilometers per second, is not just a speed. It is the speed at which information, matter, energy, and causality itself can travel through spacetime. No particle can outrun light. No signal can leap ahead of it. This is Einstein's most famous boundary, woven directly into the geometry of the universe. But the expansion of space is not motion through spacetime. It is the evolution of spacetime. And that difference changes everything. Imagine two galaxies sitting on the surface of a balloon. They are motionless relative to the rubber. They don't crawl across it. They simply rest on top of it. When you inflate the balloon, they drift apart because the rubber stretches. Their separation increases, but neither galaxy ever moved. The balloon expanded around them. The universe behaves the same way, except the balloon is not expanding into anything. Space doesn't need a surrounding environment to stretch. It expands by changing its own scale, quietly increasing the distance between any 2 points that are not gravitationally bound. When cosmologists talk about galaxies receding faster than light, they are describing this growth of scale, not motion across a surface. A galaxy that is 10 billion light-years away experiences twice as much stretching per second as one 5 billion light-years away. The farther something is, the faster it appears to recede. Eventually, that recession speed surpasses the speed of light. And yet, no cosmic law is violated. To understand why, consider the cosmic speed limit more carefully. Einstein's boundary states that no signal can travel through space faster than light. But the expansion of space is not a signal. It is not a force. It is not a flow of energy or matter. It is a change in the metric, the mathematical fabric that tells spacetime how to measure distance. The speed of expansion is measured not in kilometers per second, but in kilometers per second per megaparsec. That means for every megaparsec, about 3.26 million light-years of separation, you get a certain amount of recession speed. This is the Hubble-Lemaître constant. In the modern universe, the value is around 70 km/s per megaparsec. In the early universe, it was much higher. And during inflation, it was so enormous that space expanded exponentially, doubling in size again and again in less than a trillionth of a second. During inflation, regions of space receded from one another so quickly that it wasn't even meaningful to compare their speeds. Distances grew faster than any light beam could cross them, yet no laws were broken because nothing traveled. The metric simply rewrote the definition of distance. Here's a quiet way to visualize it. Imagine you stand on a long, silent walkway, a moving sidewalk in an empty terminal. The sidewalk moves gently beneath your feet. If you walk on it, your speed through the terminal depends on your own motion plus the motion of the walkway. But you could also stand perfectly still and still be carried along. If the walkway sped up enough, you would drift faster than your legs could ever carry you. And yet you would feel no wind, no acceleration, no resistance. Space is that walkway. Every galaxy is standing still on it, but the walkway's speed increases with distance. The paradox emerges because we instinctively think of space as a stage made of nothing, an emptiness that cannot move. But in relativity, space has properties. It can bend, stretch, fluctuate, and evolve. The cosmic microwave background, the afterglow of the Big Bang, shows that space has a temperature. Quantum mechanics shows it has energy. Gravity shows it has curvature. Since space is something, not nothing, it can change. And because it's not a physical object moving through a medium, its change is not limited by the speed of light. This is why distant galaxies slip beyond our cosmic horizon. Light leaving those galaxies today will never reach us, not because they are outrunning their own photons, but because the space between us expands faster than the photons can cross it. Each second, the light travels a certain distance toward us, but that same region of space grows by a larger amount. The photon gains ground, yet loses more ground simultaneously. This creates a horizon, a boundary beyond which events are forever unreachable. Nothing beyond that horizon can ever send a signal that reaches you. In this way, expansion quietly shapes the limits of what is observable, what is knowable, and what is physically meaningful. And as expansion accelerates, the horizon creeps closer. This is one of the strangest predictions of cosmology. In trillions of years, the Milky Way and its neighboring galaxies will be the only things visible in the night sky. All others will fade into darkness, carried beyond the shrinking horizon by dark energy. Future astronomers, if any remain, may never know that the universe once held hundreds of billions of galaxies. They will see only a lonely island of stars. This solitude does not come from the galaxies speeding away by choice. It comes from the stretching of space, a quiet, relentless widening of the cosmic grid. But even as distant galaxies recede faster than light, everything inside a gravitationally bound region remains stable. The expansion of the universe cannot pull apart the solar system. It cannot loosen the orbit of Earth. It cannot stretch an atom. Local forces, gravity, electromagnetism, nuclear binding, overpower expansion on small scales. Only the vast intergalactic emptiness is affected. This reveals something profound. Expansion is not a universal push. It is a large-scale phenomenon, sculpted by geometry rather than force. And that geometry responds to energy density, including the mysterious dark energy that now permeates space. Dark energy has a peculiar property. It exerts negative pressure. Instead of slowing expansion, it accelerates it. As the universe grows, more space forms and therefore more dark energy appears. This feedback loop causes the expansion to speed up, a cosmic acceleration that grows larger with time. This accelerated expansion is the reason galaxies can recede faster than light. It is not their motion, It is the rate of space's growth. It is geometry unfolding under its own laws. When we observe this unfolding, we are not seeing galaxies in flight. We are seeing the rhythm of spacetime itself. And so, the paradox dissolves. Nothing breaks the speed of light. Nothing violates relativity. Instead, the universe quietly reveals a deeper truth. The laws of physics limit how things move within space, but they do not limit how space itself evolves. In this widening, this soft drifting apart, the universe defines its shape, its limits, and its future. And as we drift deeper into this expanding cosmos, one question naturally rises. If space can outrun light, what happens to the galaxies that disappear beyond our cosmic horizon? Part 4. What is the Hubble constant, and why does it matter? In the 1920s, Edwin Hubble made a quiet discovery that changed everything. The farther a galaxy is, the faster it seems to be receding. That pattern, now encoded in what we call the Hubble constant, became the first measurement of cosmic expansion. But today, two methods of measuring this number disagree, and hidden in that disagreement may be clues about new physics. To understand why this constant matters, we begin with its simplest meaning. The Hubble constant tells us how quickly the universe expands at this moment in cosmic history. It connects distance to recession speed, not because galaxies are flying away from us through space, but because space itself is stretching between them. The constant is expressed in kilometers per second per megaparsec. How many kilometers per second of recession you get for every megaparsec? About 3.26 million light-years of separation. If the Hubble constant were small, distant galaxies would drift away slowly, like lanterns floating down a calm river. If it were larger, the river would be faster, carrying galaxies out of reach more quickly. But the value is not just about speed. It reveals the age, size, and fate of the universe. It tells us how long the expansion has been happening and how that expansion is changing over time. When Hubble made his discovery, the constant was incredibly uncertain. His earliest calculations suggested the universe was only about 2 billion years old, far younger than the Earth itself, which was already known to be older. Something was wrong. Only decades later, thanks to better distance measurements and a deeper understanding of stars, did astronomers realize Hubble's value had been off by a factor of about 7. Modern observations now place the universe's age at about 13.8 billion years, but the Hubble constant remains at the center of a new uncertainty. Today, two methods measure this constant, and they do not agree. The first method looks at the nearby universe. It measures distances to galaxies using standard candles. Objects such as Cepheid variable stars or type Ia supernovae, whose intrinsic brightness is well known. By comparing how bright they appear to how bright they truly are, astronomers calculate their distance. Then they measure how fast these galaxies recede using their redshift. Plot distance against speed, and the slope of that line gives the Hubble constant. This approach, called the distance ladder, yields a value around 73 kilometers per second per megaparsec. It indicates a slightly faster expansion rate. The second method looks not at nearby galaxies, but at the entire observable universe. It uses the cosmic microwave background, the cooled radiation left over from the Big Bang, as a snapshot of the early cosmos. Satellites like the European Space Agency's Planck Observatory measure the tiny temperature fluctuations across this ancient light. Those patterns reveal the density, composition, and geometry of the universe shortly after it began. When cosmologists feed that information into models of cosmic evolution, they derive a Hubble constant close to 67 kilometers per second per megaparsec. These two numbers differ by about 9%, a small amount mathematically, yet enormous scientifically. Because this disagreement is not due to measurement error alone. Over the past decade, both methods have become incredibly precise. Telescopes have improved, calibration, techniques have evolved, and independent teams have repeated the measurements countless times. The uncertainty bars shrank. The discrepancy remained. This is what scientists call the Hubble tension. If the universe were a musical instrument, the Hubble constant would be its tuning note. the pitch that reveals how all other instruments align. When two carefully tuned methods disagree on that pitch, the discord suggests either that one instrument is off or that the instrument itself, the universe, has deeper layers of structure than we realized. To grasp why this tension matters, imagine you are reading the universe like a storybook. The cosmic microwave background shows you the first chapter, an early universe governed by simple rules, radiation dominated, matter forming, dark matter emerging. The local universe shows you the later chapters, filled with galaxies, stars, and dark energy accelerating expansion. The Hubble constant is the bridge between those chapters. If the bridge doesn't line up, it means the story might contain a twist we haven't yet understood. One possibility is that dark energy might not be constant. Perhaps it has evolved over time, changing the rate of expansion in ways our models have not accounted for. Another possibility is the existence of new particles, like a form of early dark energy that briefly altered expansion before disappearing. Some theories propose that neutrinos, nearly massless particles that fill the universe, might behave differently than we expect. Others suggest tiny variations in inflation, the rapid expansion after the Big Bang, could ripple forward into how we measure the cosmic scale today. Even more exotic ideas explore modifications to gravity itself. General relativity has passed every test we've thrown at it, but the largest cosmic scales are difficult to probe. If gravity behaves differently across billions of light years, the Hubble tension might be the first whisper of that deviation. Of course, there remains a quieter possibility, that the tension is a measurement artifact. The distance ladder relies on complex calibrations, how Cepheids behave, how dust dims their light, how supernovae vary. The cosmic microwave background relies on assumptions built into cosmological models. Perhaps one of these assumptions needs adjusting. Perhaps both methods are correct within their own domains, but speak slightly different cosmological dialects. Yet, the tension has grown more persistent, not less. It has resisted correction long enough that many physicists now consider it one of the most intriguing problems in cosmology. The importance of the Hubble constant goes beyond mathematics. It touches how we understand time itself. A faster expansion rate means a younger universe. A slower rate means an older one. Even small differences ripple across billions of years, shifting estimates for when stars formed, how galaxies assembled, and when cosmic structures emerged. Our entire timeline of the universe depends on this one number. And the number is not static. The Hubble constant is the expansion rate today. In the early universe, expansion was far faster. In the distant future, it will accelerate due to dark energy. The constant we measure is a snapshot of one cosmic moment, just as a heartbeat is one instant in the rhythm of a life. This makes the tension even more compelling. If the early universe and the modern universe disagree on the expansion rate, perhaps something changed between then and now, something our equations have yet to include. Imagine looking across a quiet lake. Near the shore, the ripples behave one way. In the distance, they behave another. You assume the water is uniform, but the patterns whisper that something beneath the surface is different, something hidden that shapes the ripples as they travel. The Hubble constant is the whisper. The tension is the hidden shape. And so, this quiet disagreement between measurements has become one of the most important questions in cosmology. Not because the number itself is mysterious, but because the universe rarely disagrees with itself. When it does, it means a deeper truth is waiting. As we continue this journey through cosmic expansion, one question naturally rises. If this constant shapes our understanding of the universe's growth, what mysterious force is accelerating that growth even now? Part 5. What is dark energy and why does it accelerate the universe? In 1998, astronomers studying distant supernovae found something unexpected. The universe wasn't just expanding, it was speeding up. The cause was a mysterious pressure woven into empty space itself, now called dark energy. It acts like a quiet push, subtle yet relentless, stretching the cosmos faster with every passing moment. To understand dark energy, we must begin with the supernovae themselves. the brilliant deaths of massive stars. These explosions, especially a type known as type Ia supernovae, behave like cosmic mile markers. Their peak brightness is remarkably uniform, making them what astronomers call standard candles. When we measure their apparent brightness, we can infer how far away they are. When we measure their redshift, we can determine how fast the galaxy that hosts them is receding. In the 1990s, two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, observed dozens of these distant explosions. They expected to find that the universe's expansion was slowing, tugged backward by gravity over billions of years. Instead, the supernovae were dimmer than predicted. They were farther away than they should be. The expansion had not slowed down, it had sped up. This discovery was so unexpected that even the scientists doubted their results at first. But repeated measurements confirmed the finding. The universe was accelerating, and no known form of matter or energy could explain it. To understand why, recall how gravity works on the largest scales. Every bit of matter, stars, galaxies, dark matter, pulls every other bit inward. Over time, this pull should slow the expansion of the universe, just as throwing a ball upward eventually brings it back down. If there had been enough matter, the expansion might have halted or reversed. If there were too little matter, the expansion might have continued, but at a decreasing rate. Acceleration was the one outcome nobody expected. Something had to be counteracting gravity. Something had to be pushing space itself outward. That something is dark energy. Dark energy is not a substance we can bottle or detect directly. It does not clump into galaxies. It does not shine or absorb light. It does not behave like matter or radiation. Instead, dark energy behaves like a property of space, an intrinsic energy that exists even in perfect vacuum. The idea that empty space has energy traces back to quantum theory. Even when matter is stripped away, quantum fields remain. These fields fluctuate constantly, producing fleeting virtual particles that appear and vanish in less than a trillionth of a second. The combined energy of these fluctuations is immense on small scales, though for reasons still not understood, most of this energy seems to cancel out, but not completely. A small residue remains, small enough to escape our experiments, but large enough to influence the cosmos. In Einstein's equations of general relativity, this energy appears as a constant, the cosmological constant. It acts as a negative pressure, a kind of anti-gravity that pushes instead of pulls. If this constant is positive, it causes the expansion of the universe to accelerate, and that is exactly what we observe. But calling dark energy a constant is only one possibility. It may instead be a dynamic field, something that changes over time, similar to the field that powered inflation in the early universe. This alternative is called quintessence, and though we have no direct evidence for it yet, it remains one of the most studied models in modern cosmology. Whichever form it takes, dark energy dominates everything. Today, about 68% of the total energy content of the universe is dark energy. Matter, stars, planets, gas, dark matter, makes up the remaining 32%. Ordinary matter, the stuff of atoms, contributes less than 5%. This means the universe is ruled not by what we can see, but by what we cannot. Dark energy's effect reveals itself not in galaxies, but in the vast emptiness between them. Within galaxies, gravity binds everything too tightly for expansion to matter. Stars orbit their centers, planets orbit stars. Atoms remain untouched. But between clusters of galaxies where gravity weakens, dark energy takes over. There, space stretches more quickly over time, carrying clusters apart and thinning the cosmic web, and the acceleration grows stronger as the universe grows larger. This feedback effect is one of the most unsettling aspects of dark energy. As more space forms, more room exists for dark energy to act, and its influence increases. The accelerating expansion is not constant, it compounds. To see how dramatic this effect becomes, imagine watching two distant galaxies a billion light-years apart. As dark energy pushes them outward, the space between them stretches. In a few billion years, that space doubles. Then, The doubled space doubles again. Eventually, these galaxies recede faster than any light beam could bridge. They slip beyond the cosmic horizon, becoming unobservable forever. This slow disappearance of galaxies is one of the quiet consequences of dark energy. The universe will not end with a single cataclysm. Instead, it will fade. More and more galaxies will drift out of view. The night sky will grow emptier. In trillions of years, only the galaxies gravitationally bound to ours will remain visible. Everything else will sink beyond the horizon of space. But the mystery of dark energy deepens when we look back into the early universe. The cosmic microwave background, the afterglow of the Big Bang, contains subtle patterns that reveal the density of matter and the curvature of space. When scientists analyze these patterns, they find that dark energy must have been much weaker in the early universe. Matter dominated then. Gravity sculpted the cosmic web. Galaxies formed, stars ignited, and planets coalesced. Only when the universe grew dilute enough did dark energy rise to prominence, overtaking matter and seizing control of expansion. This transition happened around 5 billion years ago, a quiet handoff of cosmic authority. But why did dark energy become important exactly then? Why not sooner? Why not later? Cosmologists call this the cosmic coincidence problem. It is one of the reasons many suspect that dark energy may not be constant at all, but the evolving echo of some deeper physics. We know dark energy accelerates the universe. We know it behaves like negative pressure. We know it dominates the cosmic energy budget. But we do not know its origin. We do not know its composition. We do not know whether it is truly constant or slowly changing. It is the most powerful, pervasive, and mysterious phenomenon in cosmology. Even the name dark energy is a quiet admission of our ignorance. It tells us nothing of what the phenomenon is, only what it does. It darkens our understanding. It energizes the universe. It pushes the cosmos outward. Yet despite its mystery, dark energy shapes everything we observe. It determines the size of the observable universe. It dictates the cosmic horizon. It influences the growth of galaxies and the fate of all structures. It may determine how the universe ends, whether it expands forever or ruptures in a distant epoch. Dark energy is not a footnote in cosmic evolution. It is the author dragging the universe into its future. As we drift deeper into that future, one question naturally rises. If empty space is never truly empty, where does this strange energy come from, and why does the vacuum itself possess structure? Part 6. Why does empty space have energy? Quantum physics tells us that even a perfect vacuum isn't truly empty. It flickers with virtual particles that appear and vanish, carrying tiny bursts of energy. When we add up the effects of countless such fluctuations across the universe, we get the strange idea that space itself has an energy density, one that might be responsible for the universe's accelerating growth. To understand why emptiness is never truly empty, you must first let go of the classical idea of nothingness. In everyday experience, empty space feels like absence, no air, no dust, no warmth, no light. A vacuum chamber, when sealed and drained, becomes silent and bare. But quantum mechanics looks deeper than human perception. It peers into the smallest scales of existence, scales far too tiny for atoms or even electrons. There, emptiness becomes restless. At these scales, quantum fields fill every corner of the universe. They are not optional or confined to matter. They are the fundamental stage upon which matter and forces arise. These fields cannot sit perfectly still. They vibrate with inherent uncertainty, an unavoidable jitter written into the fabric of reality. Because of this uncertainty, brief fluctuations of energy occur even in the absence of particles. Virtual particles emerge from these fluctuations, borrowing energy from the vacuum and returning it in less than a heartbeat of time, so quickly that they cannot be directly observed. This ceaseless activity is called vacuum energy, and it is the first hint that the void is not truly void. But why must fields fluctuate at all? The answer lies in the uncertainty principle, one of the most profound truths in quantum theory. It states that the more precisely we know one property of a system, the less precisely we can know another. For empty space, this means that if the energy were exactly zero, the uncertainty would also need to be zero. But that is forbidden. Perfect stillness violates the rules of quantum existence, so even the vacuum must tremble. These tremors are unimaginably small on human scales, yet they occur everywhere, all the time across the cosmos. They create tiny pairs of particles and antiparticles, virtual particles, that appear, interact, and vanish almost instantly. Their fleeting presence generates an energy density that permeates every point in space. One of the most striking demonstrations of vacuum energy appears in a phenomenon called the Casimir effect. When two metal plates are placed extremely close together in a vacuum, they experience a slight attraction. Not because of any external force, but because the vacuum between the plates supports fewer quantum fluctuations than the space outside them. The imbalance pushes the plates together. It is a physical, measurable effect produced by the energy of empty space. This phenomenon, though subtle, proves an extraordinary truth. The vacuum is active, it has structure, it has influence. Yet, when physicists attempt to calculate the total energy of the vacuum using quantum field theory, something staggering happens. The predicted energy density is enormous, far greater than what we observe in cosmic expansion. If that calculated energy were real, the universe would have torn itself apart almost instantly after forming. Everything would have exploded outward too fast for matter to coalesce, too fast for galaxies to form, too fast for stars, planets, or life to arise. But the universe did not behave that way. Instead, its expansion was relatively slow for billions of years, accelerating only recently. The actual vacuum energy we infer today, what we call dark energy, is astonishingly small compared to quantum predictions, smaller by a factor of around 120. This mismatch is often called the worst theoretical prediction in the history of physics. It hints that something about our understanding of vacuum energy remains incomplete. Still, the idea that empty space has energy aligns beautifully with Einstein's equations of general relativity. In his framework, energy, even the energy of the vacuum, bends spacetime. A vacuum with positive energy causes space to expand, and if that energy is constant everywhere, the expansion will accelerate. This is precisely what astronomers observe. So the vacuum energy of quantum mechanics becomes the cosmological constant of general relativity, a bridge between the very small and the very large. But why does the vacuum's energy affect space this way? To understand this, think of spacetime as a flexible fabric. Mass and energy tell the fabric how to curve. A positive energy density and negative pressure, which vacuum energy possesses, creates a repulsive effect, not like a force pushing objects apart, but like a stretch applied to the fabric itself. As the fabric stretches, distances grow, and the stretching promotes even more stretching. This is the signature of dark energy. The universe expands faster, not because something pushes the galaxies, but because the vacuum encourages expansion. As space grows, so does the vacuum energy within it, leading to more stretching. It is a gentle feedback loop, a quiet runaway effect unfolding over billions of years. But the question remains, why does the vacuum have the particular energy density we observe? Not zero, not infinite, but a very specific, incredibly small value. There are several possibilities, each more intriguing than the last. One explanation is that the vacuum energy may be the residual effect of cosmic inflation. In the earliest fraction of a second, a high-energy vacuum state drove inflation, an extremely rapid expansion that smoothed and shaped the universe. When inflation ended, most of that vacuum energy decayed, but perhaps a small leftover fragment remains today, acting as dark energy. Another possibility is that dark energy is not constant at all. It may be dynamic, a slowly evolving field called quintessence. Unlike the cosmological constant, quintessence could change over time, possibly explaining why cosmic acceleration began only a few billion years ago, not earlier. A third idea is that the vacuum energy we observe is not fundamental, but is tied to the curvature of space itself. As the geometry of the universe evolves, the effective energy of the vacuum might shift in response. Others propose that vacuum energy might be linked to extra dimensions, hidden aspects of spacetime accessible only at extreme energies. These dimensions, if they exist, could dilute the vacuum's true value, leaving us with a faint residue. Some physicists even explore the possibility that our universe is part of a multiverse, and that the vacuum energy we observe is simply the one that allowed galaxies and observers to form. Universes with vastly different vacuum energies may exist, but they remain forever inaccessible. Despite these possibilities, vacuum energy's most extraordinary property is that it is everywhere. It fills the vast voids between galaxies. It fills the spaces inside atoms. It fills the very room around you now. Even if nothing else were present, it cannot be removed, emptied, or shielded. The vacuum is not a container. It is the foundation. Because empty space has energy, the universe has no true state of rest. Expansion continues. The horizon grows. The cosmos evolves not only because of matter, radiation, or gravity, but because the vacuum itself participates in the story. The realization that nothingness has power, gentle, omnipresent, and enduring, shifts our understanding of the universe. It tells us that even silence contains motion, even stillness contains energy, even emptiness contains structure. And as we follow this quiet thread of vacuum energy across cosmic time, one question naturally rises. If space has energy, and that energy shapes the universe, how far does its influence reach, and what lies beyond the horizon it creates? Part 7. What is the cosmic horizon, and why can't we see beyond it? Because space expands faster than light at great distances, there are regions of the universe whose light will never reach us. This boundary is called the cosmic horizon, not a wall, but a limit drawn by motion. Beyond it, galaxies drift into permanent invisibility, slipping quietly out of the observable universe. To understand the horizon, imagine standing on a vast plain shrouded in soft morning fog. The ground beneath your feet is clear. A few meters away, shapes remain visible. But far beyond that, the fog thickens into pale brightness, and the landscape simply dissolves. Nothing blocks your view. There is no barrier or gate. Yet your sight has a boundary, an edge where the world fades, not because the world ends, but because light cannot reach you. The cosmic horizon is that quiet boundary on the grandest scale imaginable. It is the eyes distance beyond which even the fastest messenger in the universe, light, cannot reach us, not now, not ever. And the reason lies not in the darkness of space, but in its expansion. As the universe grows, regions far enough away recede at such speed that any photon they emit is slowly swept back by the expanding fabric before it can make progress toward us. This concept can feel strange because our intuition was built inside a world where distances never change on their own. But once the expansion of space becomes faster than the movement of light across it, even photons lose the race. They are like swimmers attempting to swim upstream as the river's current grows stronger with each passing moment. The cosmic horizon marks the point where the river becomes uncrossable. But to see how this boundary forms, we must first distinguish between two related ideas, the observable universe and the entire universe. The observable universe is simply the region from which light has had enough time to reach us since the Big Bang, about 13.8 billion years. But because space itself stretches, the farthest objects we can see today are not 13.8 billion light-years away. They are about 46 billion light-years away. Their light was emitted when the universe was young, but as that light traveled toward us, space expanded beneath it, stretching the journey. Everything beyond this radius lies outside our observable sphere. It isn't necessarily missing. It isn't forbidden. It's simply out of reach. The cosmic horizon, however, is slightly different. It is not determined by the age of the universe, but by the rate of expansion. It is the distance beyond which light emitted now will never reach us, no matter how long the universe lasts. This distance defines our future visibility, what parts of the cosmos we are forever cut off from, not because time is too short, but because expansion is too strong. These two boundaries, the observable universe and the cosmic horizon, overlap but are not identical. One is the limit of what we can see now, the other is the limit of what we can ever see. And the cosmic horizon shrinks in one sense, more galaxies slip beyond it every day. A distant galaxy might still be visible now because its ancient light is reaching us, but the light it emits today is lost forever, dragged back by expansion. Eventually, even the old photons will stop arriving. Like a candle carried over a hill, it does not vanish instantly, but its glow fades until it disappears entirely. This slow disappearance is one of the most poignant consequences of cosmic acceleration. To understand why this happens, imagine a photon leaving a distant galaxy. At first, it travels toward us, closing the distance. But the universe is expanding as the photon moves, stretching the space ahead of it. As the photon approaches regions farther from its point of origin, those regions begin receding faster and faster. The closer the photon gets to us, the more the expansion around it changes. If the expansion rate is mild, the photon eventually arrives. If the expansion rate is strong enough, the horizon lies between the photon and us, and the light never crosses that invisible boundary. The horizon is not fixed, though. It depends on the properties of the universe, its matter density, its dark energy density, and the curvature of spacetime. As dark energy takes over and accelerates expansion, the horizon becomes more prominent, because the stretching of space gains power with time. This creates a gentle but profound isolation. Galaxies far from our own cluster will slip beyond visibility. One by one, they will drift into the cosmic dusk, leaving future astronomers with an increasingly empty sky. In trillions of years, only the galaxies gravitationally bound to our local group will still be visible. The rest of the universe will recede into a soft, eternal darkness. This is not an abrupt disappearance. It is a slow fading, a quiet unwinding of cosmic connection. A photon that leaves a distant galaxy today may travel for eons, stretching thinner and redder with every billion years of journeying, until its wavelength grows so long it becomes undetectable. The universe does not erase these photons with violence. It stretches them into invisibility. Yet even though we cannot see beyond the horizon, we can use mathematics and the cosmic microwave background to infer that the universe continues far beyond what is visible. The patterns in that ancient light indicate that space is remarkably flat. In geometry, flatness implies something infinite or nearly so. A cosmos that curves too sharply would reveal its curvature through the microwave background's temperature variations, but those variations are small. This suggests an enormous, perhaps endless universe beyond our sight. The cosmic horizon, then, is not the edge of the universe. It is the edge of our vision. But even this vision is deeply nuanced. There are actually several types of horizons in cosmology: particle horizons, event horizons, Hubble horizons, each describing different boundaries of observability or influence. The cosmic event horizon is the one tied to the accelerating universe. It tells us which galaxies will forever be causally disconnected from us. The particle horizon, by contrast, tells us the limit of what we can see today based on how long light has been traveling. It grows over time, while the event horizon remains a limit that some objects move beyond. If this seems intricate, it is because the geometry of spacetime is not intuitive. Horizons in cosmology do not resemble borders or shells. They are more like boundaries of potential communication, lines drawn by the speed of light and the changing shape of space. And we live in a universe where space is no longer merely expanding, but accelerating. That acceleration ensures that the cosmic horizon will become more important with time. It is the horizon that dictates the future of visibility. As long as dark energy behaves the way current observations suggest, the horizon will continue to limit what can ever reach us, no matter how long we wait. This truth invites a quiet reflection. We live in a universe we can never fully see. Our instruments, no matter how advanced, are bound by the laws of spacetime. Even if humanity survived for trillions of years, even if our descendants built telescopes the size of solar systems, they would still face the same horizon. There are places in the universe whose light is forever barred from us. The horizon is not a failing of our tools. It is a feature of the cosmos. To gaze at the night sky is to look at only a thin slice of a far larger whole. The universe stretches out beyond our cosmic horizon like an ocean beyond a misted shore. We cannot see it, but we know it continues. Its silence does not imply its absence. And as we contemplate this boundary of light and distance and time, one question naturally rises. If galaxies can slip beyond our horizon, what does that mean for the fate of the structures bound together within it? Part 8. Why do distant galaxies look frozen in time? When the James Webb Space Telescope peers deep into space, it also peers deep into time. Light from the farthest galaxies left them billions of years ago, long before Earth existed. As the universe expands faster, that ancient light stretches into longer wavelengths, redder and softer, carrying the cosmos's earliest memories in its fading glow. To understand why these distant galaxies appear frozen, almost suspended in the young universe, you must hold a quiet truth. Light does not move instantly. It travels at a finite speed, even when the distances are vast and the darkness endless. And in a universe where distances grow as light travels through them, the journey becomes even longer and more complex. Imagine looking across a calm lake at dawn. The far shore reflects the first hints of sunlight, but what you see is not the shore as it is now. It is the shore as it was moments ago when the light first touched it. Now, replace the lake with the cosmos and the moments with billions of years. Every distant galaxy is a shoreline seen through time. This is why the James Webb Space Telescope, orbiting quietly around the Sun, can photograph galaxies as they were only a few 100 million years after the Big Bang. Not because it reaches backward in time, but because the light reaching us now began its journey that long ago. But why do these galaxies look frozen, as if caught in a cosmic photograph? Why do we never see them as they are today? The answer lies in both distance and expansion. The farther away a galaxy is, the longer ago its light began traveling toward us. But in the time that light was traveling, the universe continued to expand. The space between galaxies did not remain fixed. It stretched. The photons were pulled along, lengthening their wavelengths, slowing their arrival, delaying their story. The galaxies we see at the edge of visibility are not ancient leaves drifting toward us. They are distant lanterns whose light struggles to cross an ever-widening sea. As the universe expands faster, that crossing becomes even more delayed. The photons stretch into redder wavelengths, into infrared, into microwaves, sometimes into wavelengths too soft to detect. The light loses energy but keeps carrying information. That fading glow becomes a time capsule. This is why the universe becomes redder the farther we look. Not because the galaxies are slowing or cooling, but because the fabric of space between us grows while the light is en route. The galaxies appear frozen because the photons we receive today represent a single chapter of their long story, a chapter written billions of years ago. The galaxies themselves have continued to evolve, forming stars, colliding with neighbors, drifting through their own cosmic web. But those later stories have not reached us yet. The universe has not allowed their later light to bridge the expanding distance, and for some galaxies, it never will. There exists a distant population of galaxies whose early light is just now reaching us, but whose more recent light is receding too quickly, swept away by expansion. They are already slipping beyond our cosmic horizon. We see them as infants, but we will never see them grow old. The universe removes them from our future sight, not suddenly, but gently, by allowing space to outrun their photons. This creates an eerie effect. The farthest galaxies we observe are perpetually young. No matter how long we wait, we will never see them in maturity. Their images are fixed in cosmic childhood, preserved by the speed of light and the relentless widening of space. This is not stillness in the galaxies themselves. It is stillness in our ability to witness them. The deeper we look, the younger the universe appears. Near us, galaxies are massive, structured, and ancient. They have spun for billions of years. They have endured collisions and mergers. They have built grand spirals and luminous cores, but far away, billions of light years away, we see primordial structures, compact, chaotic, full of newborn stars and turbulent gas. These galaxies exist in the early universe, long before heavy elements were abundant, long before spiral arms unfurled in graceful patterns. Because the speed of light is finite and the universe expands, we observe these galaxies in a cosmic freeze frame. The James Webb Space Telescope enhances this effect. Its extraordinary sensitivity to infrared light allows it to see photons that have been stretched by cosmic expansion for more than 13 billion years. These photons began as ultraviolet radiation from the first stars, but the universe's growth has lengthened them into soft infrared wavelengths Webb can detect. It is not seeing galaxies as they are. It is seeing their earliest chapters whispered across vast stretches of time. There is another layer to this frozen effect, cosmological time dilation. When a galaxy is far enough away, the expansion of space not only stretches its light, it stretches the passage of time itself as observed from here. A supernova in a distant galaxy appears to unfold more slowly. A star-forming region brightens and fades over a longer period. Cosmic processes that would take 1 month in the galaxy's own time span take 2 months or more when viewed from Earth. This dilation means that when we observe distant galaxies, we see their evolution slowed. Their internal rhythms are stretched, softened by expansion. They appear frozen not only because they are young, but because their time flows at a different apparent pace in our frame of reference. The result is a universe with layers of time embedded within it. Nearby galaxies show us the universe as it is. Mid-distance galaxies show us the universe in its adolescence, and extreme distant galaxies show us the universe in its infancy, trembling with the first sparks of starlight. This stratification is one of the quietest wonders of cosmology. The night sky is not a single moment. It is a spectrum of moments, layered across billions of years. When you look at the sky, you are not witnessing one universe. You are witnessing many at once, each representing a different chapter of cosmic evolution. The galaxies appear frozen because their stories reach us only in fragments. And beyond the farthest visible galaxies lies a darkness we can never illuminate, not because light is absent, but because the expansion of space ensures that the later stories of those galaxies will never arrive. Their photons today are being carried away faster than they can approach us. Their futures are beyond our reach. Yet we know they continue. Galaxies do not end because they pass beyond our horizon. They evolve, collide, ignite, and dim. Their stories continue in parallel with ours. We simply lose sight of them, as if walking on a vast plain where the curvature of the horizon hides distant travelers from view. Understanding this frozen appearance invites a deeper reflection. The universe is not static, but our vision of it is bound by time. Every glance into the sky is a look into the past. What we see is not what is, but what was. And this leads naturally to the next question in our quiet exploration. If distant galaxies appear frozen in their youth, how will the accelerating expansion of the universe shape the fate of galaxies that remain bound together? Part 9. Will accelerating expansion tear galaxies apart? Gravity binds stars into galaxies, galaxies into clusters, and clusters into larger structures. Yet dark energy pulls everything outward. For now, gravity wins on small scales. But in trillions of years, this balance may shift. Some models predict a future where even galaxies, atoms, and spacetime itself could be stretched beyond recognition in an event called the Big Rip. To understand whether accelerating expansion can tear galaxies apart, we must begin with the nature of the forces involved. Gravity is the quiet architect of structure. It draws matter into clumps, compressing clouds into stars, gathering stars into spirals and ellipses, and weaving galaxies into the cosmic web. Wherever matter becomes dense enough, gravity tightens its grip, forming long-lasting islands of stability. Dark energy, on the other hand, acts everywhere. It is not concentrated. It does not cling to matter. It does not diminish with distance. Instead, it behaves like a uniform pressure spread across the fabric of space, gently encouraging the expansion of the universe. Today, dark energy dominates cosmic behavior, making up nearly 70% of the universe's total energy content. The balance between these two, gravity and dark energy, determines the fate of structures across the cosmos. On small scales, gravity remains strong. The gravitational pull that binds Earth to the Sun is billions of times stronger than the outward tug of dark energy across that same distance. Even our Milky Way galaxy, 100,000 light-years across, is held together so tightly that dark energy barely affects it. To disrupt the galaxy, dark energy would have to overpower trillions upon trillions of solar masses connected by a complex web of gravitational bonds. For now, this is impossible. But the universe does not remain static. Dark energy continuously influences the large-scale expansion. As space expands, there becomes more space for dark energy to act upon. Its push strengthens, not as a force, but as a geometric effect. In the distant future, this could lead to consequences that seem unthinkable today. To explore these possibilities, cosmologists imagine different scenarios based on the properties of dark energy. If dark energy is truly constant, Einstein's cosmological constant, then the expansion will continue to accelerate, but gently. Distant galaxies will drift farther apart, eventually crossing the cosmic horizon. But local structures like galaxies and clusters will remain intact forever. Gravity will preserve these islands of matter even as the wider universe thins into emptiness. However, if dark energy is not constant, if it grows stronger with time, the story changes dramatically. Some theories propose that dark energy's pressure may increase as the universe expands, becoming more negative and more dominant. This hypothetical form of dark energy, often called phantom energy, leads to one of the most dramatic predicted endings of the universe: the Big Rip. In the Big Rip scenario, dark energy does not merely accelerate the expansion, it accelerates it at an ever-increasing rate, faster than any exponential growth. The fabric of space stretches not gently, but violently, with the rate of stretching itself accelerating without bound. If this model is correct, the universe would not fade quietly into darkness. Instead, expansion would become so intense that it would tear apart structures at every scale. But before imagining such an ending, it's helpful to walk slowly through what that process would look like, moment by moment, trillions of years into the future. First, galaxy clusters would dissolve. The gravitational glue binding them together would weaken relative to the expanding space between them. The galaxies within these clusters, once moving in slow, elegant orbits, would drift away from one another, losing their shared gravitational home. A little later, individual galaxies would face the same fate. Though immensely dense and gravitationally robust today, they would eventually become vulnerable to the accelerating expansion. The stars orbiting the galactic center would find their orbits disrupted. The galaxy's luminous spiral arms would unravel, stretching toward infinity. At a more distant time still, the solar systems within galaxies would be torn apart. Stars and their planets, once bound by deep gravitational wells, would detach. Planets would drift into darkness, no longer tethered to their suns. Stars themselves would become isolated lanterns, fading into the accelerating void. And then, as expansion grew even more catastrophic, stars themselves would not be safe. The forces within them, the fusion processes balancing gravity with outward pressure, would become disrupted. The delicate equilibrium that allows a star to shine would collapse. In the final moments before the Big Rip, even atoms would fall victim. The electromagnetic forces binding electrons to nuclei would fail. Atoms would be torn apart. Nuclei would disintegrate. Protons and neutrons would dissolve into quarks, which would then be pulled apart by the rapidly stretching spacetime. Eventually, even spacetime itself, its geometry so distorted by runaway acceleration, would cease to behave in any predictable way. The universe would end in an infinite tearing, every structure shredded by the accelerating expansion. This is the most extreme possibility, beautiful in its symmetry, sobering in its implications, and deeply speculative. Most cosmologists do not expect the Big Rip to occur, because current measurements of dark energy suggest a value very close to the cosmological constant. If dark energy remains constant, the universe will expand forever, but gently, without tearing galaxies or atoms apart. Instead, clusters will separate, galaxies will drift apart, stars will age, burn out, and cool. Black holes will eventually evaporate through Hawking radiation. Over unimaginable spans of time, the universe will become increasingly diffuse until nearly all energy is stretched across an almost infinite expanse of emptiness. But even in this calmer scenario, sometimes called the Big Freeze, the accelerating expansion ensures that the cosmic horizon will shrink. More galaxies will slip beyond visibility. The night sky will grow darker. Future observers might see only the remnants of their own galaxy, unaware of the vast cosmic structures that once surrounded them. Still, on human timescales, and even on the timescales of stars and galaxies, dark energy is gentle. It poses no threat to our galaxy in the foreseeable future. It does not pull at stars within the Milky Way. It does not loosen the orbits of planets. It does not stretch planets or atoms or people. Its influence becomes overwhelming only across immense distances, distances we will never experience directly. Gravity and dark energy coexist quietly for now. Gravity rules the small and the dense. Dark energy rules the vast and the empty. Their interplay shapes the future of the cosmos. Understanding whether dark energy might someday grow strong enough to tear galaxies apart remains one of the deepest questions in cosmology, because the answer depends on discovering what dark energy truly is. Is it a constant, a field, a property of spacetime that changes over time? We do not yet know. But the possibility of a future where expansion overwhelms every structure invites one lingering question. If expansion can grow strong enough to tear galaxies apart, why doesn't it affect our solar system or even smaller systems right now? Part 10. Is the expansion uniform everywhere? Even as the cosmos accelerates, it does so smoothly and evenly on the largest scales. But locally, space behaves differently. Gravity gathers matter into clusters and filaments, creating islands of structure surrounded by oceans of expansion. The universe is not stretching like a balloon. It's stretching like a woven fabric where the fibers hold their shape even as the whole cloth grows. To understand this delicate balance between uniformity and structure, imagine standing close to a tightly woven tapestry. Up close, you see threads pulled taut, intersections holding firm, knots resisting any tug from the fabric around them. But if you step back, the tapestry as a whole can shift, stretch, or hang differently without altering the woven patterns inside it. The universe behaves in much the same way. On the largest scales, the scales measured in hundreds of millions of light years, the universe is astonishingly uniform. Its expansion is not chaotic or directional. It unfolds evenly, the same in every direction, a smooth stretching encoded in the laws of general relativity. This uniformity is not merely a philosophical statement. It is measured in the cosmic microwave background, the faint fossil glow of the Big Bang. The temperature of this ancient radiation varies by less than a few parts in 100,000. That near-perfect smoothness strongly suggests that on cosmic scales, space expands evenly. But when we zoom in, when we explore the universe in detail, we see that the expansion is not felt everywhere equally. Instead, we find a cosmic web, long filaments of galaxies, vast clusters bound by their shared gravity, and even emptier voids stretching between them. The universe is lumpy. Matter is not distributed like mist, it is structured like an intricate, branching network. In the dense regions of this network, gravity overwhelms expansion. Inside galaxies, stars orbit their centers in stable paths. Inside solar systems, planets remain bound to their stars. Even between neighboring galaxies within the same cluster, gravity holds sway. The expansion of space does not tear these structures apart because their bonds are stronger than the quiet outward drift of the cosmos. This creates a layered behavior. On small scales, the universe is static. On large scales, it is stretching. Between these two regimes lies a subtle boundary, a region where neither gravity nor expansion completely dominates. Understanding why expansion is uniform on large scales begins with a period called cosmic inflation, a burst of exponential expansion that took place less than a trillionth of a second after the Big Bang. Inflation smoothed the universe, ironing out any early wrinkles and distributing matter and energy nearly evenly across all of space. That smoothing set the foundation for a universe that looks remarkably similar in every direction when viewed at great distances. But inflation also planted tiny seeds, minute fluctuations in density, microscopic ripples in the early fabric of space. Over billions of years, gravity amplified these tiny variations. Regions that were slightly denser attracted more matter, becoming galaxies and clusters. Regions that were slightly emptier grew into the vast voids that dominate the cosmic landscape. Thus, the universe acquired its web-like structure. This duality, smooth on large scales, structured on small ones, is one of the defining features of cosmology. Imagine a vast ocean. When you stand at its shore, waves break and swirl around your feet. Locally, the water's anything but calm. But far out on the horizon, the surface looks flat, smooth, uniform. The apparent contradiction dissolves when you recognize that local forces, wind, tides, currents, shape the waves, while the ocean as a whole remains steady. The universe behaves the same way. Local disturbances, gravity, star formation, galactic motion create complexity. But the expansion, the widening of space itself, remains tranquil, and even on scales where individual galaxies blend into a cosmic haze. This is why astronomers say the universe is homogeneous and isotropic on large scales. Homogeneous because every region of the universe, averaged over hundreds of millions of light years, contains the same amount of matter. Isotropic because the universe looks the same in every direction. But this smooth expansion raises a quiet question. How can the cosmic fabric stretch evenly if parts of that fabric are not stretching at all? The answer lies in the nature of spacetime. Expansion is not a force that pulls on objects. It is a change in geometry. Matter, by curving spacetime, creates local pockets where that geometry behaves differently. A massive galaxy cluster, for example, curves spacetime so strongly that its inner region remains untouched by the stretching of the cosmic fabric. The expansion simply does not operate there in any significant way. In contrast, the vast voids between clusters experience almost pure expansion. These voids grow larger over time, their emptiness expanding more noticeably than the structured regions. In fact, voids expand faster than the universe as a whole. They become the dominant feature of large-scale structure, pushing clusters and filaments farther apart. This interplay can be visualized with another metaphor. Imagine a sheet of bread dough sprinkled with seeds. As the dough rises, it expands uniformly. But the seeds, representing galaxies and clusters, remain the same size. They do not stretch. They simply drift apart as the dough between them expands. Yet, the cosmic dough does not rise perfectly evenly. Regions with more seeds, more matter, rise less because gravity pushes back. Regions with fewer seeds rise more. The overall pattern is uniform, but the local behavior varies with density. This leads us to a subtle truth. Expansion is uniform only when viewed from far enough away. Up close, the universe is a patchwork of stability and motion. Dense regions resist expansion. Empty regions encourage it. This difference explains why galaxies do not expand internally, why solar systems remain stable, and why atoms are not torn apart by the growth of space. When we observe the expansion's uniformity, we are looking at an average across vast distances. Just as the Earth appears smooth from orbit, even though mountains and valleys break its surface, the universe appears smooth on scales, where its local complexities blend into a larger pattern. Understanding this smooth expansion reveals something else. The universe's fate depends not only on the existence of dark energy, but on its uniformity. If dark energy remains evenly distributed, the universe will continue expanding smoothly, with gravitationally bound regions slowly becoming more isolated. But if dark energy varies in density across space, a possibility explored in some theories, then different regions of the universe might evolve at different rates. For now, all evidence suggests dark energy is uniform, just like the expansion it drives. But the possibility of variation keeps cosmologists curious, prompting deeper studies of the cosmic microwave background and the distribution of galaxies. The uniform expansion also shapes how we perceive the distant universe. When we measure redshifts, the stretching of light, we assume expansion is uniform. When we estimate cosmic distances, we rely on that assumption. The uniformity of expansion is the quiet foundation upon which the entire field of observational cosmology rests. And yet, the textured universe we live in, the one shaped by gravity's intricate web, reminds us that uniformity is only half the story. The universe expands smoothly everywhere, but it expands differently somewhere depending on what occupies that region. It is a vast woven fabric with tight knots and loose spaces, yet the entire cloth stretches together, guided by the same cosmic law. This gentle interplay of smoothness and structure leads inevitably to the next question. If expansion leaves small systems untouched, why doesn't the universe's growth pull our solar system, or even our atoms, slowly apart? Part 11. Why doesn't expansion happen inside our solar system? If the universe is expanding, why doesn't Earth move away from the Sun? Why don't atoms expand? The reason is simple. Gravity and electromagnetism bind small systems tightly enough to resist cosmic stretching. Expansion only becomes noticeable across truly vast distances, where galaxies themselves act like drifting lanterns in an ever-widening sea. To understand why expansion does not affect our solar system, you must first understand how the expansion operates. It is not a force acting upon objects. It is a change in the geometry of space, the gradual stretching of the metric that defines distance. But this stretching is incredibly weak on small scales. The size of the effect is proportional to distance. The larger the separation between two objects, the more noticeable the expansion becomes. On small scales, the effect is not simply weak, it is overwhelmed entirely. Imagine a gentle tide rising beneath you. If you stand on a rock close to the shore, the water may swirl around your feet, but it cannot lift the rock. The rock's weight, its density, anchors it firmly in place. Expansion is like that tide, rising beneath galaxies, but unable to budge the dense knots of matter bound tightly by gravity or electromagnetism. Now, consider Earth's orbit. Gravity binds Earth to the Sun with enormous strength. The gravitational pull between them is far greater than the stretching effect of cosmic expansion across one astronomical unit, the distance between Earth and the Sun. If expansion were the only factor, that distance would grow by a tiny fraction of a millimeter per year. But gravity exerts a force trillions of times stronger than that. Expansion becomes irrelevant. This is why planets remain in orbit. This is why solar systems remain intact. The strength of their internal bonds dominates the geometry of the surrounding space. The same logic applies to atoms. Electromagnetic forces bind electrons to their nuclei. These forces are so much stronger than cosmic expansion that the gap between a proton and an electron cannot be stretched, even in principle. Electrons do not drift outward. Molecules do not swell. The expansion of the universe is not trying to stretch them at all. It operates only over distances large enough for gravitational or electromagnetic bonds to weaken. The truth is that expansion only influences systems once their internal forces drop below a certain threshold. It requires emptiness, it requires distance, it requires vast regions with little matter. This is why expansion is felt between galaxies and galaxy clusters. These are the regions where emptiness dominates, where the pull of gravity weakens across millions of light years, leaving space free to stretch. Inside the Milky Way, however, there is no emptiness large enough to feel expansion. The gravitational potential of the galaxy acts like an anchor. It curves spacetime strongly enough that the metric stretching becomes negligible. All stars orbit the galactic center, bound by a collective mass of hundreds of billions of suns. Even the empty gaps between stars are not empty enough. Though enormous on human scales, a few light years is insignificant compared to the scales where expansion becomes noticeable. The gravitational influence of the galaxy binds these regions too. The stretching of space is far too gentle to disrupt stellar orbits. This layered influence of gravity creates a quiet hierarchy in the universe. At the smallest scale, atoms hold firm against everything. At a larger scale, molecules remain intact, unaffected by cosmic changes. Solar systems are stable, galaxies remain cohesive. Only beyond the confines of galaxies, in the enormous intergalactic voids, does expansion dominate. To see this more clearly, imagine the universe as a vast sponge. The sponge itself expands, its soft, porous structure widening in all directions. But the water droplets clinging to the fibers, the galaxies, solar systems, atoms, do not expand. They are bound by their own forces. The sponge grows around them, but they maintain their shape. They drift apart only because the material between them grows. This metaphor echoes a deeper truth. Expansion is the widening of emptiness, not the stretching of matter. The boundaries of gravitationally bound systems define the scales at which expansion ceases to operate. Inside these regions, space-time is curved enough that expansion does not have the freedom to stretch distances. The geometry bends inward, holding matter together. Outside these regions, where matter thins and curvature fades, expansion takes the lead. The boundary between these regimes is expressed mathematically through general relativity. The acceleration caused by dark energy is extremely small compared to local gravitational accelerations. Dark energy becomes important only on scales larger than galaxy clusters. It affects them gently, slowly pushing them apart, but it cannot overcome the gravity of a galaxy, let alone a solar system. Even if dark energy grows stronger over cosmic time, as in some models of phantom energy, the dominance only becomes relevant trillions or quadrillions of years from now. At present, and for far more time than humanity can imagine, the solar system remains firmly shielded from expansion. The Milky Way remains safe. Even the local group of galaxies, our small cosmic neighborhood, will remain gravitationally bound for as long as physics predicts its existence. It is only the very largest structures that yield to expansion. The superclusters, the filaments, the walls of galaxies stretched between tremendous voids. These structures are already drifting away from us faster than we can ever chase. They are the lanterns drifting on the widening sea. The distinction between expansion at large scales and stasis at small scales reveals something profound about the universe. The cosmic fabric does not stretch uniformly through everything. It stretches through nothingness. It fills the gaps between the islands of matter. It shapes the broad outline of the cosmos while leaving the small details untouched. This is why astronomers say the universe is expanding, but they also say that atoms, planets, and stars remain unchanged. The two truths coexist, not in contradiction, but in harmony. They describe different layers of reality, each governed by forces that dominate at that scale. Understanding the limits of cosmic expansion invites a quieter reflection on our place in this enormous universe. We live not in the drifting emptiness, but in one of the tightly bound islands. A small planet in a stable orbit inside a calm solar system within a swirling galaxy. An island safely anchored amid the widening tides of space. This stability allows life to unfold. It allows stars to burn steadily, planets to hold atmospheres, and atoms to remain intact for billions of years. The universe expands, but its expansion leaves pockets of stillness where complexity can arise. And so one question naturally rises as we continue our journey through this layered cosmos. If expansion leaves small systems untouched, how did inflation manage to stretch the entire universe so violently in its earliest fraction of a second? Part 12. What role did inflation play in shaping expansion? Before the universe was even a second old, it underwent inflation, a burst of expansion so rapid that regions once smaller than atoms grew faster than the speed of light. This early surge smoothed the cosmos, flattened space, and planted the seeds of all future structures. Today's expansion is gentler, a quiet echo of that primeval eruption. To understand inflation, you must picture the universe not as a vast expanse, but as something unimaginably tiny, far smaller than a proton, far smaller than anything you could ever hope to observe. In this early moment, the universe was dense, hot, and trembling with quantum fluctuations. It wasn't empty space expanding, it was space itself coming into existence, realm by realm, moment by moment. Then, something extraordinary happened. A form of energy unlike anything we experience today came to dominate. This energy, associated with a field we call the inflaton, possessed a pressure so negative that it caused spacetime to stretch at a staggering rate. In less than a trillionth of a second, the universe grew from subatomic scale to macroscopic size, expanding by a factor so large that ordinary numbers barely describe it. Inflation did not push matter outward. It did not fling particles across space. Instead, it stretched space itself. And because space can expand faster than light without breaking the laws of physics, inflation outran all possible motion, erasing any irregularities and smoothing out the early universe into near-perfect uniformity. Before inflation, the young cosmos may have been curved, chaotic, or uneven. Inflation flattened it, it cooled it, it wiped away ancient wrinkles as effortlessly as a warm breeze smoothing a fogged window. This flattening is not a metaphor. It is a measurable feature. Observations of the cosmic microwave background, ancient light released 380,000 years after the Big Bang, show that the geometry of the universe is remarkably flat, far flatter than would be expected without some dramatic early event. The simplest explanation is inflation. Only a burst of rapid expansion could have stretched the geometry into the near-perfect uniformity we observe today. But at the same time, inflation smoothed the cosmos. It also created its imperfections. Quantum fluctuations in the inflaton field, tiny jitters at the smallest scales, were stretched to cosmic size. These fluctuations became the seeds of all future structure. Regions slightly denser than average gathered matter through gravity, forming galaxies, stars, and planets. Regions slightly less dense became cosmic voids. The universe today, its filaments, clusters, and swirling galaxies, is the magnified imprint of those ancient quantum tremors. This dual nature of inflation, smoothing the universe while seeding its structure, is one of the most remarkable insights in cosmology. The tiniest fluctuations in the earliest instant became the grand architecture of everything we see. But inflation also shaped the future of cosmic expansion. When inflation ended, the inflaton field decayed. Its energy was released into particles, radiation, and matter. The universe reheated violently, filling with the ingredients that would eventually form stars and galaxies. But inflation did not vanish without a trace. It left behind a universe primed for expansion, with space already stretching and matter already distributed evenly across enormous distances. The expansion we see today is a gentle continuation, an echo, faint but persistent, of that primordial surge. Dark energy now drives the acceleration, not the inflaton field, but the geometry, the smoothness, the flatness, the horizon, all were shaped by inflation's imprint. Understanding inflation also helps explain why distant regions of the cosmos look so similar. When we observe opposite sides of the sky, separated by tens of billions of light years, we find the cosmic microwave background has nearly identical temperatures. Yet those regions are so far apart that no light or signal could have traveled between them in the time since the Big Bang. How, then, could they have reached such perfect equilibrium? Inflation answers this elegantly. Before inflation, the universe was tiny enough for all its parts to interact and reach thermal balance. During inflation, these well-mixed regions were torn apart faster than light could travel, preserving their uniformity across vast stretches of space. The horizon problem, the question of why distant regions match so precisely, dissolves when inflation is included. This smoothing effect also explains the universe's immense size. Without inflation, the cosmos would be far smaller today. Inflation granted it the head start required for billions of years of growth to produce the vast cosmic web we observe. But inflation's influence reaches further still. It set the stage for the dominance of dark energy. Because inflation made space so flat and uniform, dark energy could later operate evenly across the cosmos, driving a gentle acceleration on large scales. Without inflation's smoothing, later expansion might have unfolded irregularly, shaped by pockets of curvature and uneven distribution of matter. In this way, inflation and dark energy are distant cousins, both driving expansion, one violently and briefly, the other softly and endlessly. Yet inflation remains one of the most mysterious chapters of cosmic history. We know it occurred because its fingerprints are everywhere in the universe, but we do not know what caused it. The inflaton field is hypothetical, its energy scale is unknown, its decay mechanism remains theoretical. Inflation may have been triggered by high-energy physics we have not yet uncovered, or it may be the manifestation of a deeper principle woven into the structure of spacetime. Some theories propose that inflation may be eternal, that while it ended in our region of space, it continues elsewhere, spawning a multiverse of bubble universes. Each bubble grows from its own inflationary seed, forming a cosmos with its own physical laws and constants. In this view, our universe is one region of a vastly larger inflationary landscape. Whether or not this is true, inflation's impact cannot be overstated. It determined the size, shape, structure, and future of the cosmos. It is the silent architect behind the large-scale universe, and though it lasted for only a fraction of a second, its consequences are eternal. As expansion continues today, slowly, gently, guided by dark energy, it carries the memory of inflation's first breath. The geometry shaped in that explosive moment still governs the paths of galaxies and the limits of our horizon. Inflation did more than stretch space. It set the initial conditions for everything that followed. It determined the cosmic stage upon which stars ignite, planets spin, and life eventually emerges. It transformed the universe from quantum foam into a vast, coherent expanse capable of forming complexity. And as we drift forward in this quiet exploration of cosmic expansion, one question naturally rises. If inflation once stretched the universe so dramatically, could expansion ever stop or reverse someday in the far future? Part 13. Why does acceleration imply a strange fate for time itself? As the universe expands faster, distant regions fall out of causal contact. Time in those places drifts away from ours, not through clocks or gravity, but through separation. In an accelerating cosmos, two observers separated by enough space will no longer share the same future, each carried down a different branch of cosmic time. To understand why acceleration reshapes time, you must imagine time as more than the ticking of a clock or the turning of a planet. Time in relativity is woven into space-time itself. It stretches, curves, and diverges depending on the paths objects follow through the cosmos. When expansion accelerates, these paths bend outward, away from one another, like lines drawn on an inflating balloon. And as they diverge, the flow of time along them begins to diverge as well. This divergence does not involve slowing clocks or speeding ones. It emerges from something subtler, the loss of shared events. In relativity, time is defined not just by ticking, but by connections, by the possibility of sending signals, exchanging information, sharing a future. When two regions of space grow so far apart that light can no longer travel between them, their futures become disconnected. Their timelines fork. This is the quiet consequence of acceleration, not a distortion of time, but a separation of time. In a decelerating universe, even very distant galaxies remain causally linked. Their light might take longer and longer to reach us, but it can still, eventually, arrive. There is still a shared future, a possibility of communication, however faint. But in an accelerating universe, the distance between galaxies grows faster than light can cross it. Beyond a certain point, the expansion of space outruns even the universe's ultimate speed limit. Light emitted today from those regions will never reach us, and our light will never reach them. This boundary is the cosmic event horizon. Everything beyond it becomes permanently unreachable. We can see their early light emitted billions of years ago, long before acceleration took hold, but we cannot see their present, and we will never see their future. From their perspective, the same is true of us. As acceleration continues, galaxies that remain within our horizon will eventually slide beyond it. Their fate becomes sealed. They will drift into a darkness where our timeline cannot follow. They will not disappear in a dramatic instant. They will fade as their light stretches, reddens, and softens until even the last photon becomes undetectable. When that happens, our future no longer includes them. Their future no longer includes us. Their branch of cosmic time diverges into a separate reality. This branching raises an unusual question. What does it mean for two regions of the universe to no longer share the same future? The answer lies in the geometry of spacetime. In relativity, time is not universal. It depends on the structure of spacetime itself, on which events can influence which other events. If two regions cannot exchange signals, they cannot influence each other's evolution. Their histories separate. Acceleration sharpens this separation. Imagine two travelers walking on a vast plain. At first, they walk side by side. Then, slowly, the terrain beneath them begins moving. One is carried onto a rising hill. The other drifts onto a gentle slope. As the ground beneath them continues to reshape itself, they move farther apart, even if they never take a step. Eventually, each stands on a different horizon, surrounded by a landscape the other will never see again. This is what accelerated expansion does to cosmic time. It moves the ground beneath observers, pulling their timelines apart. Two galaxies that were once linked by light become isolated, each carried along its own track of spacetime, each with its own future light cone, its own region of potential influence. They no longer share a common future. This fate is not limited to distant galaxies. It applies to entire civilizations, entire clusters, entire domains of the universe. The accelerating expansion ensures that the universe's far future will fragment into countless isolated islands of spacetime, each with its own distinct thread of time, each unable to see or influence any other. Time at the cosmic level becomes local. To observers in one region, the universe will appear to grow darker, quieter, emptier. More and more galaxies will slip beyond the horizon. The cosmic web will thin until only the gravitationally bound structures, galaxies, clusters, and groups remain visible. Eventually, even these structures will stop receiving the early light of the expanding universe. They will drift in an island of darkness, a pocket of space-time cut off from all others. Inside these islands, time will still flow normally. Clocks will tick, stars will shine, planets will orbit, but only within the bounds of that island. Outside it, the rest of the universe will exist on another thread of time, unreachable and invisible. This fragmentation of time is one of the quietest and most profound consequences of acceleration. It means that the universe will not end in a single moment. It will end gradually, through a soft and gentle severing of connections. And as these connections fade, the meaning of future becomes more local. In the distant cosmic night, each island will possess its own future, its own timeline, shaped only by the matter within it, untouched by anything beyond its shrinking horizon. This individualization of cosmic time does not contradict general relativity. It flows directly from it. Causal contact, who can talk with whom, defines time's reach. Acceleration limits that reach. The faster the expansion grows, the faster horizons shrink, and the faster time itself fractures into separate domains. Today, with the universe still young on cosmic timescales, we still share a vast common future. Billions of galaxies remain within our horizon. Signals sent now can still cross enormous portions of the cosmos. Our cosmic time is wide and connected. But in trillions of years, the horizon will shrink so dramatically that only our local group of galaxies will remain accessible. All other timelines will float silently beyond the edge of observability. Their futures will drift away from ours like ships lost in an endless fog. This raises a philosophical question. If two regions of the universe no longer share events, do they still share the same time? Relativity suggests that time is defined by events and influence. If no events can be shared, their times diverge. They do not contradict each other. They simply belong to different pathways. Acceleration ensures that more and more regions will slip onto these separate pathways. In the end, the accelerating universe becomes a quiet archipelago of timelines, each isolated, each drifting deeper into the silence of its own future. Time does not end, but it fractures into countless branches. And this leads naturally to the next question on our journey. If the universe is accelerating and time is branching, what does this imply about how large the cosmos truly is? Part 14. Could the expansion someday reverse? For decades, cosmologists wondered whether gravity might slow the universe's growth and eventually pull it back inward. But the discovery of dark energy changed that dream. Today, all evidence suggests the expansion will not only continue, it will accelerate indefinitely. Yet some theories allow for shifts in dark energy that could someday stop or even reverse the expansion, rewriting cosmic history. For much of the 20th century, the idea of a cosmic reversal, known as the Big Crunch, was a compelling possibility. In this vision, the universe expands after the Big Bang, slows under the pull of gravity, halts, and then contracts. Galaxies would begin drifting inward, cosmic structures would draw together, the expansion would give way to collapse. Ultimately, everything would converge into a final singularity, mirroring the conditions of the Big Bang in reverse. In that era, the key unknown was the density of matter in the universe. If enough mass existed, if galaxies, dark matter, and all unseen forms of energy added up to a critical threshold, then gravity would eventually overcome expansion. The universe might stretch for billions of years, but ultimately it would fall back on itself. But if the matter density was lower than this threshold, expansion would continue forever, slowing but never stopping. This simple dichotomy, collapse or endless expansion, was once at the heart of cosmology. Everything depended on the balance between gravity and expansion. Then, in 1998, the discovery of accelerating expansion upended this picture. Dark energy entered the story, and with it came a profound shift in how we understand the universe's fate. Instead of slowing down, the expansion was speeding up. Gravity, no matter how much matter existed, could not reverse the expansion unless dark energy itself weakened dramatically. The dream of a big crunch faded, not because it became impossible, but because acceleration overcame the competing forces. Still, the question remains, could the expansion someday reverse? Could dark energy change over time, altering the cosmic trajectory in ways we cannot yet foresee? To explore this possibility, we must first recognize that dark energy is not fully understood. Its nature, origin, and evolution are still unknown. We measure its effects, but not its essence. And depending on what it is, its future could unfold in several very different ways. One possibility is that dark energy is truly constant, a fixed property of spacetime known as the cosmological constant. If this is correct, expansion will accelerate forever. The universe will grow colder, darker, and more isolated, drifting toward a distant future, sometimes called the heat death or the big freeze. But dark energy might not be constant. It might evolve, it might weaken, it might strengthen, it might even reverse in sign. Consider the scenario in which dark energy is a dynamic field, something like quintessence, whose strength changes with time. If this field gradually loses energy, its repulsive effect would diminish. Expansion might slow. The cosmic acceleration we observe today could be temporary. Over trillions of years, the universe might return to a slower expansion or even a steady one. Gravity could begin to play a larger role again. If dark energy weakened enough, gravity might halt expansion entirely. Galaxies might stop drifting apart. The cosmic horizon might stop shrinking. A balance could emerge, a universe poised on a subtle edge between expansion and contraction. And if the field continued to weaken beyond this balance point, the universe could begin collapsing, pulled inward by its own gravity. In such a scenario, cosmic time would unwind in a new direction. Galaxies would move closer. The large-scale structure of the universe would begin to compress. Clusters would merge. Temperatures would rise as matter became increasingly dense. Stars would be torn apart. Black holes might merge, releasing immense waves of gravitational radiation. Eventually, everything would converge into a final singularity, a mirror of the Big Bang known as the Big Crunch. This possibility is not ruled out. It is simply less likely given current measurements. But with mysteries surrounding dark energy, certainty remains elusive. There is also another possibility, more exotic and deeply intriguing. Dark energy could change sign. Today, it acts as a negative pressure, driving expansion. But in some theoretical models, dark energy could evolve into a positive pressure, a force that pulls inward instead of pushing outward. If that happened, expansion would not merely slow, it would reverse abruptly. The universe could transition from acceleration to collapse as if a cosmic switch were thrown. Instead of drifting apart, galaxies would rush together. The collapse would be swift, dramatic, and universal. This shift might occur if dark energy is linked to fields that oscillate or decay, or if the vacuum state of the universe transitions to a lower energy configuration, a phase change akin to water freezing or evaporating. There is even a theory that the universe might eventually tunnel into a new vacuum state, a quantum event that would rewrite the laws of physics instantaneously across the cosmos. In such a scenario, expansion might halt entirely as space itself undergoes a fundamental transformation. This is more speculative, but it highlights how complex the question becomes when quantum mechanics enters cosmology. Still, these reversal scenarios face a major challenge. The observed value of dark energy today seems extremely stable. Measurements of the expansion rate, the cosmic microwave background, and the distribution of galaxies all suggest that dark energy is not changing noticeably over billions of years. If it changes at all, it changes slowly, far too slowly to reverse expansion any time in the foreseeable cosmic future. Yet, foreseeable is a very small word in a universe that may exist for trillions upon trillions of years. Dark energy could evolve on cosmic timescales we cannot directly observe. There is another perspective to consider: multiple phases of cosmic history. The universe has already experienced rapid expansion during inflation, followed by decelerating expansion, followed by accelerating expansion. This suggests that the cosmos may not be confined to a single mode. Expansion might evolve through several phases. Some we have experienced, others we have not yet reached. In this view, a future reversal is not impossible. It is simply one of several potential futures, depending on how dark energy behaves over eons. Inflation proved that the universe can undergo dramatic bursts of expansion. Dark energy proves it can accelerate gently over billions of years. Gravity proves it can slow expansion under the right conditions. These ingredients suggest a cosmos capable of complex evolution, not a simple path toward one inevitable fate. And so the question, could expansion someday reverse, remains open, balanced between observation and imagination. What we can say with confidence is this: today's expansion is accelerating. For the foreseeable future, everything we see suggests acceleration will continue. The cosmic horizon will shrink. More galaxies will drift beyond visibility. The universe will become darker and quieter. But beyond that horizon, beyond trillions of years, the behavior of dark energy remains an unsolved riddle. Cosmologists study the universe not only to understand its past, but to glimpse its future, and in that spirit, the possibility of Chondover. Reversal, however distant, invites a quiet and profound question as we move toward the final part of this journey. If the universe's expansion might one day reverse, or continue forever, or change in ways we cannot yet predict, what does that say about the true size of the cosmos we inhabit? Part 15. What does an accelerating universe mean for the very distant future? Far beyond the lifetime of stars, beyond the cooling of galaxies, the accelerating universe will keep stretching. Over unimaginable spans of time, light itself will thin, galaxies will drift alone, and the universe will grow quieter. Expansion becomes a slow, soft fade, an ending not with violence, but with distance, as the cosmos relaxes into an ever-widening silence. To understand the far future of an accelerating universe, we must first imagine a timescale so vast that ordinary numbers feel small against it. Human history spans only thousands of years. Civilizations rise and fall in the blink of cosmic time. Even stars, those ancient furnaces burning for billions of years, shine for only a moment compared to the universe's grand timeline. But acceleration stretches the future even more dramatically. As space expands faster, it creates longer eras of isolation, longer nights, longer silences. The universe will not end in fire, nor in a single catastrophic collapse. Instead, it will end through separation, a slow drifting apart of everything that once shared the same cosmic home. This quiet unraveling begins with the galaxies. Today, galaxies gather in clusters bound by gravity. Our own Milky Way belongs to a cluster called the Local Group, a small island of stars and dark matter drifting through the cosmic ocean. Beyond our local group lie other clusters, connected by filaments, separated by voids. But as the universe accelerates, those clusters drift away faster than light can bridge the gap. Their light will fade. Their presence will slowly slide beyond our cosmic horizon. In a few 100 billion years, observers within the local group, if any remain, will see an empty sky. The once rich tapestry of galaxies will have dissolved into darkness. Only the galaxies gravitationally bound to our own will remain visible. The acceleration does not tear these galaxies apart. Gravity is too strong. The stars inside them stay in orbit. The planets remain steady. But the cosmic web unravels, strand by strand, until only isolated knots remain. The night sky becomes the quietest it has ever been. As time passes, even these last galaxies will begin to change. Stars burn slowly, but not eternally. Massive stars die quickly, collapsing into black holes or blasting apart as supernovae. Smaller stars, the most common kind in the universe, burn for trillions of years, glowing red and dim as they age. Eventually, they exhaust their fuel. Their light fades, their heat dwindles. In the far future, the universe enters what physicists call the degenerate era, a time when all luminous stars have burned out. What remains are white dwarfs, neutron stars, and black holes, objects that shine only weakly, if at all. In this era, the accelerating universe becomes even emptier. The stars have dimmed, the galaxies have quieted. The cosmic horizon shrinks. Dark energy dominates completely, smoothing space into an almost featureless expanse. White dwarfs, once the hot glowing cores of ancient stars, cool slowly into black dwarfs, dark, cold remnants that emit almost no light. These remnants drift silently around the centers of their long-dead galaxies, their orbits unchanged, but their glow extinguished. The only remaining sources of light come from rare collisions and quantum effects, events so infrequent and faint that they barely disturb the universal silence. As the universe continues to expand, the density of matter drops further. Interactions become increasingly rare. Two stars that once might have collided over billions of years now drift so far apart that chance encounters all but vanish. Gravity's web loosens, not because it weakens, but because the distances grow so large that its influence becomes negligible beyond each tiny surviving island. The cosmos becomes a collection of isolated pockets, galactic fossils, scattered across an ever-expanding sea. Even this is not the end. Black holes, the last strongholds of gravitational strength, dominate the dark landscape for a time. They swallow stray matter. They drift in silent orbits. But even black holes are not eternal. Through Hawking radiation, an effect predicted by quantum mechanics, they slowly evaporate, emitting faint particles and energy over extraordinary timescales. A supermassive black hole might take 10 to 100 years to evaporate, a number so vast it defies the imagination. Yet in the far future, even these giants will disappear, fading into nothingness as the cosmos continues to stretch. With the final black holes gone, the universe enters its quietest age, the dark era. In this era, the cosmos consists of almost nothing. A few stray particles left from black hole evaporation. Occasional photons stretched to wavelengths larger than galaxies. The expansion, still accelerating, smears these remnants across an unfathomable expanse. The temperature of the universe approaches absolute zero. Time continues, but activity ceases. There are no stars to burn, no galaxies to shape, no black holes to anchor structure. The universe becomes more empty than any vacuum we could imagine. It becomes a vast, silent expanse with no events to mark its passing. Even light itself becomes meaningless. Photons stretch so far that their energy becomes almost zero. They cannot illuminate anything. They cannot interact with matter. They drift endlessly, their wavelengths long enough to span the cosmos itself. This is the fate of an accelerating universe, not a catastrophic end, but a gentle fading, a long sigh, a quiet dissolution of structure until only space remains, smooth, cold, and silent. But even this silence carries a kind of cosmic beauty. It reflects the strange balance between creation and dispersal, between gravity's gathering power and the expansion's quiet unraveling. The universe began in a burst of heat and light, flourished in a period of stars and galaxies, and will end in a vast, tranquil emptiness shaped by the very expansion that once allowed structure to form. Some cosmologists call this the heat death of the universe. Others call it the eternal dark. But the name is less important than the shape of the journey. The accelerating universe stretches time itself into nearly infinite horizons. It allows islands of matter to endure for eons before eventually relaxing them into silence. And in that silence, the expansion continues, not out of purpose, but out of the simple geometry of space, seeded by inflation and sustained by dark energy. Humanity, if it endures long enough, will witness only the earliest chapters of this future. Long before stars fade or galaxies drift beyond sight, our species will have changed or vanished, but the universe will continue quietly, following its own gentle trajectory. And as this long, slow ending unfolds, one truth remains clear. The universe will not end with destruction. It will end with distance, a soft fading, a quiet expansion, a final relaxation into cosmic stillness. The accelerating universe does not slam the door closed. It simply lets everything drift so far apart that the door is never needed again.